In this section, we basically have two goals. We want to be able to solve exponential equations and also be able to solve logarithmic equations. First, we're going to look at exponential equations, and it's important to realize that an exponential equation can be recognized by the fact that the variable is going to be in the exponent location whenever you look at that equation. For example, when we look at the first piece, it's 2x equals 8, where x is down below with where the coefficient 2 is, versus this problem where you have 2 raised to the x equals 8. So in the second case, the exponent is a variable. Notice it's a variable, whereas here the exponent, if you think about it, is just x raised to the 1. It's a constant. So this, of course, is a linear equation, and we would be able to solve it by just dividing both sides by 2 and getting x equals 4. This, of course, is an exponential equation, and how do we solve it? We want to have some methods for it. Right now, we can guess that x has to be 3, since 2 cubed is going to be equal to 8. So that's just a guess for this exponential equation solution, but we want to have a method to solve it. So how do we solve exponential equations? Our first goal will always be to get the same base on both sides of the equation and then use this property that says if a to the x is equal to a to the y, x must be equal to y. In other words, whatever the exponents are must be equal if the bases are to be equal. So if we can get the same base on both sides, that's always the way to go. If we can't get the same base on both sides, then we use logarithms and drop down the exponents. So we want to see example of both cases. We'll start with the first case, which is easier. Let's solve these equations. This is the case where we can get the same base on both sides. So I look at 2 and I look at 8 and I think, hey, I can rewrite 8 using a base 2. So that's my first step. Rewrite this side as a base 2. 8 is the same as 2 cubed. Once I have it in that form, this guy must be equal to that guy. The exponents, whatever they are, must be equal. So I just yank those out and solve the resulting equation, which is just going to end up being a mini linear equation. So the answer is x equal to 6. And it checks out. 6 minus 3 is 3 and 2 cubed is 8. We do the same thing for part B. I'm going to leave the 3 alone and rewrite 81 with a base of 3. So 3 to the 2x is equal to 3 to the 4th, because 81 is 3 to the 4th. And once I have that, this must be equal to this, since the bases are the same. So I have 2x equals 4, and ultimately x must be equal to 2. Okay, solve this exponential equation. I want to point out that in all of these, since x is in the exponent spot, the variable is in the exponent spot, that is what signifies it to be an exponential equation. So let's go back over here. I'm trying to solve for x, so I want to isolate this exponential term. I'm going to subtract 3 from both sides. That's 4 to the x equals 256. Now my goal is to get the same base on both sides. So 4 to the x, and I can rewrite 256 as a base 4. 4 to the 4th is actually 256. Once I write them with the same base, these two guys must be equal, and it looks like there's no more work. X has to be equal to 4. For D again, it's an exponential equation because x is in the exponent spot. Now notice I have 2 base 10s on the left. My goal is always to have one base raised to a variable, and whatever the other side is, get that to be the same base. So I'm going to add these exponents so I can merge these two into 1. So that's going to end up giving me 10 to the x plus x is 2x minus 2. And why did that happen? Well, I'm using this basic idea that if I have x squared, let's say, times x cubed, and the bases are the same, that actually ends up being x to the 5th. So this is the property I'm using. Same base, when you're multiplying, simply add the exponents. So I just added the 2 exponents. And on the right, I'm going to rewrite 1000 as a 10 cubed so that the left and the right can have only one base and both being the same base. Now this guy must be equal to this guy, and we end up with 2x minus 2 equals 3, and then from there on we isolate x, and it looks like x is equal to 5/2. Let's look at one more in the same base scenario. So in this case, notice the bases are already the same. I don't have to do any work there, and I only have one base 5 here, one base 5 there, so automatically the exponents must be equal. So 4x must be equal to x squared minus 5. That looks like a quadratic equation, so I'm going to set it equal to 0. X squared, put it the right side in descending order. And either use the quadratic formula, or if it's factorable, which it is in this case, go ahead and factor the trinomial. And it looks like I have two answers that pop out. X is either equal to 5 or x is equal to -1. Both of these are solutions to this exponential equation. Let's solve these equations. In this case, we can't get the same base, so we're going to use logs. There's no way I can rewrite 7 as a base 2, so automatically I just take log of both sides. Now I can choose to take log of both sides with the base 10. Of course, I'm not really putting it there because it's implied it's a base 10. Once I take a log of both sides, I can use this property that says, remember, log base a of x to the r, you can drop down the exponent and put it in the front. So I can use this property and drop this x in the front. That'll be x log of 2 equals log of 7. Now notice this is just a number, and so is this. They're both just numbers. So I have a linear equation, and I'm going to divide both sides by that number, and that's going to give me x equals log of 7 over log of 2. So I can write it like this in exact form, or if you choose the change of base formula, remember this could be written as log base 2 of 7 with the formula we learned in section 9.4, and you also want to be able to put it correctly into your calculator and give me an approximation. So if I punch it into my calculator, I get, remember to divide the 2, and we get approximately 2.81. So exact answer, and an approximation. Part B, I'll go ahead and do the same thing. I'll take log of both sides because I can't get the same base on both sides. And I can bring down the exponent if I want, but notice also that if the base is automatically implied to be 10, and the base and the argument's base are the same, my first piece completely disappears, and I simply get 0.4 of x, because if I bring this down also, log base 10 of 10 is just 1 anyway. So these guys completely disappear, makes it easier for me. I get log of 124, and I divide both sides by 0.4. We get, for an exact answer, log of 124 over 0.4. And then for an approximation, let's go punch it in. We get approximately 5.23. Okay, part C, again, I have an exponential equation. I want to get the exponential term by itself, so I'm going to add 4. First, that's 3.1 raised to the 2x equals 20. And since I can't get the same base on both sides, I'm just going to go ahead and take log of both sides. And since this is a base 10 and that's a 3.1, they don't go away, so this guy drops in the front. And I get 2x log of 3.1 and log of 20. Then I have my eye on the x because I want the x to be by itself. So if I want this to be alone, I have to divide by all the numbers that are stuck to it or multiplied by it. So I'm going to do it both in one step, divide by 2 times log of 3.1. So these guys divide out, and I get x equals log of 20 divided by 2 times log of 3.1. And we can also approximate it punching it in our calculator as 1.32. Let's look at one more exponential where we can't get the same base. Again, I can't get the 3 and the 5 to be the same, and it's an exponential equation because the x's are in the exponent spots. So I just go ahead and take log of both sides. Once I do that, I have access to these exponents, so I bring them down. Then log of 3 is just a number, so I'm going to distribute that number. Once I distribute that number, I have my eye on this x and this x because That's what I'm trying to solve for, so I might as well get them on the same side. So now I have all the x's on the same side, and I can't subtract log of 5 and log of 3 because they have these x's stuck to them. So I'm going to go ahead and factor that x out of both of those. Notice all I did was factor out a GCF. Now I can solve for x by dividing both sides by this ugly number. So I've got x all by itself in terms of these logs. I can simplify this a little bit. I can say I can move this exponent up and make that log of 3 squared if I want. And I can merge these guys with a division property. Log of 5 over 3 we can say. So I could also say log of 9 in the numerator and log of 5/3 in the denominator is my x value. That might be easier to punch into the calculator to get the approximation as well. So x is approximately 4.30 once we punch this or this into our calculator. Next we look at logarithmic equations, which already have the word log in the equation that you're presented with, and we want to know how to solve these. So how do we solve these? The first thing you want to do is use properties and condense the logarithms on both sides. Then do the circle if you have log on. So we do the circle that we did earlier if we have log on one side. And if we have logs on both sides, you just simply set the arguments equal. And regardless of which one you're doing, your last step is always check your solution in the original problem because you may get extraneous solutions. So condense first, and then either do this or this, depending on which case it is, then check your solution. Let's do some examples. Part A, it's a log equation because it clearly has the word log, and I don't have any condensing to do because there's only one log all by itself. I know the base is 10, so I just do the circle on it. That means 10 to the second must be x, so I have 100 equal x. And since I put it in and I get 10 log base 10 of 100 to be 2, it checks out, so I'm good to go. So mainly when I say check the solution, you want to make sure you don't get log of 0 or log of a negative number. That would be the indication that your answer doesn't work. Now part B is a little bit different because I have 2 logs on the left, so the first thing I want to do is use properties to condense the plus into a product. Very first thing you must do is condense. Once I have it condensed into one log, I only have log on one side, so I can do the circle on this guy as well and say 2 to the third must be equal to whatever that argument is. Now the logs are gone. I simplify the left, I multiply out the right side, and I can add 1 to both sides. Once I do that, I can square root both sides and I get a plus and a minus 3. The 3 works because it doesn't make any of the arguments negative. The negative 3 doesn't work because negative 3 minus 1 is negative 4, and I can't have log of a negative number, so I only keep positive 3. Okay, let's solve this log equation. First thing I must do is condense and get one log, and since it's a division, it looks like it changes into a quotient on the left. And on the right side, I have one log anyway. So since I have logs on both sides, their arguments must be equal, so I just set those guys equal to each other and I'm good to go. So this, I don't do the circle because I have logs on both sides and their arguments must be equal if their bases are the same. Thereafter I can just cross multiply. After I cross multiply, it's just a linear equation. I isolate x and I put in a 4 in here, I get a positive argument. I put a 4 in here, 4 plus 2 is a positive argument, so this must be good. Okay, one more log equation. There's nothing that I really want to condense. I want to get the log term by itself. So let me isolate the log term first. Then while I'm at it, let's divide by 2. Now I have only one log on one side. The base must have been a 10, and I can again do the circle on this. So 10 raised to the 1.4 must be x, or using our calculator, approximately 25.12.